Voilà, ben on va commencer. Donc le premier séminaire est donné par Bernard Julia. Le titre est Symmetry, Chaos and Integrability for Gravity, Exceptions Become Routine. Donc le cours est donné en français, les séminaires sont, comme vous pouvez le voir, en anglais. Donc je veux dire deux choses avant de laisser la parole à Bernard. Tout d'abord, je tenais beaucoup à ce que Bernard soit le premier orateur pour le premier séminaire du cours, dans la mesure où c'est un des pionniers du sujet. Je pense que ce sujet a vraiment véritablement décollé et démarré avec l'article dont j'ai parlé tout à l'heure de Kremer et Julia sur la réduction dimensionnelle de la supergravité à 4. Depuis lors, Bernard a énormément contribué au développement du sujet. Et je pense que son séminaire aussi va donner un très bel aperçu sur les nombreuses directions et sur les nombreux sujets importants auxquels touche l'étude de la gravitation, et en particulier des symétries de la gravitation. Il y a non seulement les symétries, mais le chaos pointe son nez. J'en ai parlé un tout petit peu, j'en dirai un petit peu plus. Bernard va en parler. Aussi l'intégrabilité, le fait qu'on a des symétries immenses fait penser à l'intégrabilité, mais est-ce qu'on a réellement des systèmes intégrables? La gravitation est vraiment très subtile et comme il est indiqué dans le titre aussi, Exceptions Become Routine. Je pense que vous en serez convaincus à la fin de cet exposé. Donc Bernard, merci beaucoup.
Merci beaucoup pour l'invitation. C'est pas moi, sorry, it's not my choice to speak in English. You will immediately notice that I have a German accent, so if you don't understand, please raise your hand. And also please ask questions all the time, because I don't know you, so it's difficult to adjust. Also, I want to say that I chose this topic of trying to reconcile both chaos and integrability, where in a situation where I'm absolutely not an expert in chaos, but I wanted that as a challenge, just to keep young and to say maybe I can contribute something new and different. So in preparing this talk, in fact, I discovered 10 problems or subjects I want to work on. And of course, I couldn't solve any of them or not even prepare all of them. So I have prepared 3 or 4. I will give you the list. And chaos, as a matter of fact, is heavily represented in the list of problems, but my understanding is not complete. So I will mention some general observations at several places, and please don't hesitate to interrupt. So also the construction of the talk was a bit difficult because I wanted to, as the title shows, to organize the talk as a kind of trying to escape from E8. So I wanted to show E8 coming back to you many times. So I did do that, but it makes it difficult to follow the other line going between chaos and integrability at the same time. So I've tried to take the first two-thirds of my talk as a regular talk. And then I have some special 3 problems or 4 that I can discuss. It depends also, I can adjust for the length. And then please ask as many questions as you want. So let me start. And again, thank you for the invitation. I had the pleasure to collaborate with Marc, and it's always impressive for me. I'm a little bit disorganized and I do many things at the same time. But if Marc is interested in something and starting to do it every week, you will see. Every time you meet him, you will see a big progress, everything written down, and it's finished in no time. So, and if he has no time, you will have a student to finish it for him. So it's very impressive and enjoyable. So to understand the talk, it's even more complicated. I tried to follow a color code. So first of all, who are going to be the players? So there is a special adversary, as I mentioned, E8. Then there is a hero. I will talk mostly about integrability and possibly relations, duality as they are related to integrability, which is not one-to-one. It's interesting, and I will mention some open questions. And then, as you know, Ulysses had to go between 2 problems. If he was looking for integrability, he had to avoid disorder or vorticity and singularity. So Marc talked about singularities. I will mention some singularities which are a bit different. Maybe they can be put together, I don't know. And then this I will talk only about supersymmetry. It's behind the scene. It's very important to explain maybe all the mysteries that are still there after 40 years or so since we discovered these exceptional groups. But the point is that there is no simple supersymmetric algebraic knowledge that tells you that what we have discovered is clear or easy to guess. I will not have time to discuss that too much, but if you classify the simple superalgebras, so algebras made out of commutators and anti-commutators, as you know, there are three or a few exceptional regular classical Lie superalgebras, and they are related to, they are called F4, G2, and another one, O2, OS2P21 alpha with a parameter, which is different from the usual bosonic simple algebras. But there's nothing with E8, E7, or any E. I will mention families of E's. So maybe we have to go to infinite dimensions, but people have tried. Katz has tried very hard. Maybe we should go to something else. They are not exactly supersymmetries, like quantum supersymmetries or other algebras. At the moment, it's a pretty open question, so we need people like you to have a fresh attempt to sort it out. So I will be your narrator, and the color code in the slides will be red for open questions, because that's maybe interesting for you, and purple is very red, so it's maybe deep questions. So it's my prejudice, there's no guarantee. So green means I have contributed partly to some of the things that are written. And blue and black, if I am following my code, are just for facts proven by other people, of course. So let's start with a picture I'm very proud of, because this picture was drawn in 1982 when I was invited to a conference in Chicago, which actually was the best conference or most stimulating conference I ever attended. It was organized by Singer, and I met Igor Frankl there. So he was a mathematician, some interest in physics, in dual string models, and I was interested in math for many years. And we had a very special interaction. He was with all his colleagues, mostly with these people who are mathematicians. And I have a very good memory of this. So in fact, I wanted to mention it. I never mentioned it in public. That I guess, I'm not sure. I was invited by Singer, whom I knew also, but on the influence of Moshe Flato, who was the assistant to Lishnarovitz right here. And because he had some talk about me with a relative of mine, Françoise, who mentioned it to me, and this all happened in Collège de France, so I'm grateful to Collège de France also for that. For this talk, I was invited by Marc, and maybe you would be interested to know that we met a long time ago in Austin in a motel in Texas, in the middle of the winter, but there's no winter in Texas. And it was all organized by Richard Feynman. So in private, I can tell you an embarrassing story about me and him, but not now. So what I'm proud of is that this cathedral actually is still there. The reason it's broken is not that there was a fire or anything, but this gap has been filled quite a bit. This is M-theory, so it has changed name, but so it's kind of rearrangement on this side. But the challenge is still there. Gravitation and quantum theory are not reconciled. So in mathematics, you would say geometry and group theory. By the way, Thurston told me once that he thought that geometry was part of physics. So he was, of course, a very famous geometer.
So the gap between Einstein and supergravities represents the lack of a quantum theory? Or?
No. It's just some geometry missing. It's just too primitive. The brains are missing. I didn't know that. Okay. So let me start easy with some background. I cannot explain everything, but I try to have snapshots of interesting piece of information, if possible in an economical way, so you can learn two things at the same time. So here I want to define what a symmetric space is in a Lie algebra, and at the same time a superalgebra structure. So both of them are decompositions of a vector space. So G is a Lie algebra or superalgebra. And it's decomposed in the case of the Cartons of the Lie algebra of ordinary Lie algebra as the maximal compact subalgebra. and an orthogonal part. There's a killing form that allows you to decompose it. And there's a Cartesian involution that is very important to determine what kg is, because the fixed point of this involution is kg. And the important distinction between kg and p is the following. The killing form is negative on kg and positive on p. So if you want to avoid ghosts, you definitely should project out one of the two. And the usual story in our picture is to project out the compact subgroup. So before my time, I think non-compact groups were pretty much to be avoided because of this ghost problem, because the killing form is not negative definite, sorry. And since we have been doing this work, of course it doesn't apply to space-time groups like Poincaré and Lorentz, but which is a different story, which is still not completely clear, again, in this unification problem I'm playing with. But right now, you understand that if you have G, which is a symmetry, and if Kg is somehow gauged, the degrees of freedom of G along Kg just don't count. So the minus sign, the ghost possibility has disappeared. It has a minus sign, but it has been erased by integration out of the gauge group. So with this definition, G over Kg is a non-compact Riemannian symmetric space. So it's non-compact because G is a non-compact form. There's a dual compact form where you take G over Kg, but Kg is not the maximal compact of G. And this story has been developed by Élie Cartan in the early part of the 20th century. Now, with the same structure, you can recognize superalgebra. So G0 is the bosonic part and a fermionic part Q. And the killing form doesn't always exist in superalgebras, even simple ones. But what you have to remember that G is acting on G0. So G0 is acting on itself, it's a subalgebra. G0 is acting on Q, it's a representation of G0, like here. And Q, now anticommutator of Q is in G0, which is non-trivial. Here, P times P is in Kg, is also non-trivial. That's what defines these non-compact Riemannian symmetric spaces. So in this commutator of two supersymmetries, usually in supergravities, what happens is QQ contains space-time translations. Sometimes these, especially if you have higher dimensions, these momentum components may become electric charge or magnetic charge. And then you will get so-called pseudo-central charges in the commutator, and you get what you may know as smaller multiplets, which are very important because they are protected from quantum corrections. Now, if you don't know symmetric spaces, let me play a little exercise that you could have tried, and I could have tried too for many years, but I didn't. It only 2 years ago, I think. So there are in simple algebras two categories, the ones that are described by ordinary numbers or almost ordinary numbers, real, complex, and quaternions. So they are respectively the orthogonal group, a unitary group, and symplectic group, which is related to complex quaternionic unitary groups. And then there are 5 exceptions. They are called E8, E7, E6, F4, and G2, as you can see there. And the question is, one of my big questions is, I want to understand why we found E7, Marc also. Nobody really understands. We discovered it by doing some counting. I will explain later. But what happens is that if E8 is so rich, it appears in many places. And if you want to understand the property of E8 that makes it appear, it's maybe useful to know if it comes with a family. So for instance, if E8, E7, E6 come together, in fact, the families tend to be larger, then it restricts the possibilities because the properties that are characteristic and used are in smaller number. And then you can try and go and understand why it appears here or in another place. So this is the work going on, and I've not written much on it. I've given talks. There are transparencies floating around now, but I think the simplest kind of family you can try is precisely to look at the symmetric spaces. So the symmetric space was G divided by Kg. Remember that?
So which real form do you consider?
I took all the possible real forms, non-compact, and I looked at symmetric spaces that could, you see, for instance, E6 has 4 descendants, and it corresponds to this decomposition. So I put G on top of or at the beginning of an arrow, and at the end of the arrow I put kg. And then I continue. And you see that there's a family that appears, E8, E7, E6, and the longest one goes through F4 and C3. And this line is actually an L in the magic square that I may have time to discuss later on. So G2 is a little bit isolated. You can see it here. When I put A1 in parentheses, it means that the maximal subgroup of E8 is E7 times A1. But when I continue, I discard A1 because it doesn't lead anywhere. So I just did that systematically. Sometimes you have D1. D1 is SO2. It's my notation. It's not a simple group, but it's U1. It's the same. So what are some properties you can be interested in? First of all, the fact that SO16, D8, is a maximal subgroup of E8, corresponds to a real form of E8, is quite important. And the fact that D8 contains D4 times D4 is also very important. These two things are more or less obvious from technical knowledge. What is less obvious is how to see D4 times D4 in E8, but it's true. And now, this is purple or red if you want. I think it's quite important to understand geometrically better why E8 contains F4 times G2. This occurs in many places. It's even important in the magic square, this construction here. And it has generalizations for other corners of the magic square. But the point is that if you have a Lie algebra, you have its Dynkin diagram. I will explain shortly what this is. And you can look at two kinds of subalgebras. Subalgebras that correspond to a subdiagram of the Dynkin diagram. These are called regular. But other regular subalgebras are also seen on the same Cartons of Algebra and same root system. But to see them in the diagram, you go first from the diagram of the group G to the diagram of the affine Casimir group, which has one more root, the rank 1 plus, the rank plus 1. And you look into that extended diagram and try to find the other regular subalgebras. But F4 times G2, they are definitely not of that type because they're not simply laced, and you need double bonds, and so it's more complicated. And in fact, I tried to ask one of the last collaborator of Dynkin who was trying to improve the root system and Dynkin diagrams when Dynkin was very, very old. He's now dead, unfortunately. So he was still looking for a better presentation of groups. So you shouldn't stop with the Dynkin diagrams. That might be a better diagram with your name. Okay, any questions here? Am I too slow? Too fast?
So red is open.
No, sorry. Here.
This is established.
No, this is all established. Yes, sorry. I used the old slides and I didn't change all the colors. I think I put in red here all these non-simply list algebras, right? But so if you want, if you follow what I said, it's also partly unknown. So I put a lot of fancy names in the first slide, and maybe you didn't understand all the names. So I explained a little bit what exceptional means. So I did do part of my job. Then I talked about Liouville. So what does Liouville have to do with this? So let me start again with Collège de France. Liouville was professor in Collège de France since 1851. This will be an important year for us. And he died in 1882, still professor in Collège de France. I think his health was not too good. The first lectures he gave in Collège de France were on integrable systems, precisely, and on elliptic functions. These lectures on elliptic functions were extraordinary. And two of the listeners did actually write them up in a book under their name. So it was a little bit controversial, but I don't know too much of the story. It's interesting. But Liouville was much well known before because, for instance, the Liouville numbers, which I'll also talk about at the end if I have time, were invented in 1844.
And who are these two persons who wrote a book under their names? You know the names?
Briot and Bouquet, yes, I will mention them. They did something very interesting. Okay, I jump ahead of myself. For those who want to leave early, this Briot and Bouquet, I claim, discovered the Weil group of E9 in 1856. So before E9, even E8 existed. So it's quite interesting to understand this. That's one of the families of E8. Maybe I will not have time, it will be at the end. So the other important observation connected to that is in the same set of equations that had this Dynkin or Val group of E9, they had the Val group of affine D4. So it's a small sequence, affine in 8, affine E7, affine E6, and affine D4. And this, for me, is telling you that D4 or SO8 is exceptional. So everybody knows it's exceptional because it's a rotation of the octonions, but this is precise meaning of exceptional because they play a special role in deep corners. So UV integrability was developed over several papers in interaction with Jacobi. So just to put you in context, Hamilton-Jacobi equation was 1833-38. Jacobi had some papers in that period, and they exchanged letters intensively. In fact, Liouville was directing the second big mathematics journal of all times, and he was working extremely hard, and he was publishing Jacobi and himself, and doing extremely good work. So before that, there was no journals. People were writing manuscripts and writing long letters. Sometimes a priest would serve as a postman or something. And it was interesting work, but not at all like internet. Another good feature of Liouville is that he actually understood that Galois was a genius, and he spent a lot of time trying to understand what he had done. And so I can just give him credit for that. So exactly at the same time, there was another professor in Collège de France who was professor of comparative law, first interested by Germany and then by the United States. In those days, in 1870, the Americans were for Germany against France. And he was very much for the United States, of course, because he knew everything about their law and their custom and their society. So he organized the collected money for constructing this statue that some of you may know. And the French paid for the top and the Americans paid for the bottom. And it was quite difficult to raise the money in the United States. So it took a long time. And he died in 1883 before it was actually realized. But it's not clear exactly how much of the precise idea was his. Bartholdi, the sculptor, also was important in making the idea more precise. But the general idea of making a present of France to the United States was his. And I take this opportunity to say that I'm very happy that although 1870 was a low point in the US-France collaboration, since January 20 this year, it's a little better. So classical integrability, I will just do trivial recollections. In fact, it's not so trivial. There is a well-known Liouville-Arnold integrability, but there are many more degrees of knowledge about integrability, partial integrability, and algebraic integrability. So let me just go through a few points. So first of all, what does it mean integrable? So first of all, it can mean solvable or integrable, but with allowed knowledge. And then you have to define what allowed knowledge is. I will give you an example for polynomials. So it's for instance, you allow algebraic operations, quadratures, but nothing else. Or you allow elliptic functions, or you allow a much larger dictionary of functions. So this is a not so clear notion. So Galois theory is solving polynomial equations, knowing roots, essentially. In fact, you know that the general fifth degree equation cannot be solved, quote unquote, in Galois theory. But actually, if you use elliptic functions, you can solve the 5-degree equation. And that I learned only recently, completely by chance. And this was done by Hermite, and also some German and Italian, I think. So transcendental values is related to this algebraic property or non-algebraic property. And transcendent functions are only partially related. Some values of transcendent functions are transcendent, and you have to define what transcendent means in each case. But it's a very open research problem right now. But doing this Galois theory for differential equations was actually the main goal of Lie. And Lie failed, but he did, of course, a lot of interesting work, and that was used 50 years later, but he was not so happy when he was alive. So the Liouville integrable system, as made more precise by Arnold, is a 2D, D is the dimension, is the number of degrees of freedom, or half the number of degrees of freedom. Dimensional Hamiltonian system with D Poisson commuting functions determining compact D tori, which admit parameters I and the angle on them, betas. And the action variables comprise the Hamiltonian. And the evolution in time of the betas, if you have this fact that they commute, can be made linear in time, or affine in time, it is AT plus B. And everything is computable by quadratures. So it's extremely special. And there was, for instance, a fashion that people were looking at solitons in the 70s, 80s. And many mathematicians would joke and say, what is this zero measure set of equations? What are you doing? But already there, then it was clear that if you had a duality, and we knew already Saint-Gordon-Tiering duality, for instance, that exchanges weak and strong coupling is extremely important to by some exact mechanism, so maybe because it's integrable or because something else. Then you can do perturbation theory on one side that tells you what the non-perturbative effects are on the other side. And we do that all the time now with strings. And of course, as I said, you can have algebraic, analytic, real analytic, differentiable, piecewise linear, and so on, versions of this integrability. And Palvé test, I have no time to explain, so it has to do with singularities. I will mention it from the side later on. So that I already said. Now, you can have duality without integrability, maybe. And let me give you just one example of a Becklund transformation. Actually, I will give it in a few slides. So the Becklund transformation is a transformation that relates two functions by, say, first-order equations, for instance, in such a way that the compatibility conditions of these equations give you, by elimination of one function, give you an equation of motion for the other, and conversely. So that relates solutions of two equations, sometimes the same equation, and that's quite important for instance, adding solitons or integrability, but it's not completely equivalent. So, in fact, I put it in red because I don't know the precise relation.
I mean, it's not equivalent because it's not always weak-strong duality.
No, I think that could be dualities, I think, where it would be just a very special property, and not the rest of the integrability would hold. Okay. But there are dualities that do not exchange strong and weak couplings also. In string theory, you have T dualities and S dualities. So both of them are possible. So I was just using the S dualities as an example of something particularly interesting, but it's not the only case. So here, what did I do? I justified Liouville and explained a little bit integrability. So I'm not completely in time. So just Becklund, let's take two scalar fields, so zero forms, A and B. And the relation between A and B is dA is dual of dB. This tilde means it's the equation of motion, or generalized equation of motion, or meaning on shells. This is a notation that's sometimes useful. And Marc would have used it this morning because he had to mix the two at some point, because he had identities and equations of motion, which were actually interestingly mixed. So the compatibility condition is just a Cauchy-Riemann equation, is the Laplace equation for B and A, or complex variables. So you have actually SO2 duality rotations between A and B. This was for scalar fields, but of course for electric and magnetic fields you have exactly the same, and everybody knows that. Unless there is a question, I will jump. So you remember I had a cathedral a while ago. So if you look a little bit, you had geometry on one side, and the fermions on the outside, guts to the top. And now it looks like a modern cathedral, but to me it looks a bit like something that's about to explode. I put a D-brain in the middle, which looks like a heart, but it's just to make you less nervous. But this is quite compact, impressive. So let me just go through it quickly. So 11 dimensional supergravity is here. plus its branes. So M2 branes, I think I proposed first in writing in 79. So at least Macduff quotes my paper in his book. And then, so this was after actually the old superstrings in 1971. Then maximal supergravity was 1978. And then there were two more theoretic strings discovered rather late. And we believe there is no more. I mean, there are a few more, but not as fundamental, and depending on compactifications of those. So I will not talk about that. And there is the open string, whose structure was also deciphered rather recently. There are many dualities between these, maybe auto-dualities or auto-Backlund. Like 2B strings is self-dual. There's T-duality between and B, you know all of that. And so it's a very compact situation. Everything seems to be equivalent to everything. So M2 brane are dual to M5 branes, for instance. But it's contrary to what you said, it's not a quantum theory of anything yet. Furthermore, the day it was discovered, I think it's 1989, that the branes were as important as strings was a catastrophe, because strings have the peculiarity that the equations are solvable, quasi-linear, linearizable, and plus interactions. But strings, membranes and higher objects are, like field theories in the higher dimensions, much more difficult. So although we started with strings, we are back in field theory, and we have to struggle. So we have strings to help on the corner, and we coupling corner, but it's not a good news. It was not a good news. It was good news for supergravity, because the branes of supergravity should also be included. And for me, it's not very different to have 11-dimensional supergravity, M2 branes and M5 branes, and maybe a little bit more, or these D branes of various types in strings. So the dualities I will have no time to explain. So everything, as I said, is dual to each other. Any question? So let me now go to E8 and try to see if I find E8 again. In fact, E8 is in several places. So theoretic strings have two possible symmetric groups, E8 cross E8, and another one is D16, which to me was not so exceptional. Both of them are exceptional in the sense of lattice theory and modular forms, but they are not so exceptional as fundamental objects. In fact, I will not have time to explain that, but for packings, it has been shown that E8 is densest packing, not only a densest lattice packing in 8 dimensions, sphere packings, but it's the densest packing of all. So it's extremely difficult to prove by analysis this. And in 24 dimensions, the Leech lattice, which is important for strings, as well as the same property, is densest than anything else. But in the middle, these two lattices are nothing special at all. So the modular invariance is not what's important, there's something else. And maybe you should learn what it is. So I am jumping to various openings. Maybe we'll find this useful. So let me go back to history, because E8 is sometimes attributed to other people. So as was said, E8 was not said, maybe. E8 was first discovered with Eugène in the first paper, or the big paper we wrote in 1979. And the only understanding a priori, the way we discovered it, was to add, rather blindly, these two numbers and find this identity that 248, as you may know, is the dimension of the adjoint representation, the smallest representation of E8. Actually, we did this for E7, because in 4 dimensions, E7 is a group. So I remember we knew 70, that's the number of scalar fields. We knew 63, it's SU8 is a R-symmetry dimension. But nobody had added this up before, and this number is, of course, the dimension of E7. Actually, I didn't know that before I did the addition. And I had to look at a book with Eugène to check this. So more precisely, we constructed, of course, the Lagrangian for E7, including fermions, and I did, just for fun, the construction of the bosonic Lagrangian of E8, which is quite interesting. You see the picture, in this case, of where E8 has a maximal compact subgroup. is that you have a so-called triangular decomposition. So E8 is essentially the maximal compact subgroup, and you don't take the orthogonal part, you take an upper triangular part. If you do that, the non-commutative terms are not general functions, they are polynomial. And that's exactly what you get when you go down from polynomial theory in higher dimension. And that's what explains that this structure is quite important. So it explains these non-compact symmetries. Let me give you two more, maybe more recent occurrences of E8. One is compact E8. It's actually not so clear. So if you look at the Ising model in the magnetic field, don't look at all the details. Alexander Zamolodchikov discovered, I don't know why, I think he had some idea because they were talking with Fateyev on this structure of conformal theory. So he's deforming a conformal theory in 2 dimensions to an integrable theory in 2 dimensions in precise sense. And he found that the spectrum after deformation was related to the eigenvector of one matrix that's important in the model, and these were exactly related to E8. So in fact there are more examples, but this is, and in fact there is a solid that has been shown to have this E8 spectrum. So it's not really E8. You find 8 numbers that are deeply related to E8, and they are the spectrum of some physical system. So that's what I mentioned already, and I can skip it. Okay. So what did I do? I added some E8s, and mostly E8s. So now the key of these dualities, E8 of course might look formidable to you, and nobody really wants to invert 248 by 248 matrices to check something. Especially, even if it's polynomial, it's not always completely polynomial, it's only the triangular part. But the maximal compact subgroup is, for in the case of E7, is a SU8 and it's a big matrix. You don't really want to do it every day. So I think the crux of the matter, the one thing I don't understand deeply in these U dualities is exemplified in the case of pure Einstein gravity reduced from 4 to 3 dimensions. The so-called Euler's duality. So let's take a moving frame of forms, EMA. So M is a curved index, A is a flat index, so 4 by 4. It decomposes into a 3 by 3 frame, maybe some rescaling here. A fourth direction of the tetrad, which will actually belong, which will actually play the role of a Maxwell 1 form in 3 dimensions. And S is a 4 last component of the scalar field. So I'm assuming that there is a killing vector that I can ignore one of the 4 coordinates. I'll take its space like it could be time-like. In the case of null, killing vector is more complicated. I have some paper on that, but I will not talk about it. Now, I talked about dualities between little a and little b before, capital A and capital B. In 3 dimensions, a scalar is dual to a 1 form. So what can we do with that? We can dualize the vector of the 1 form, and I get a second scalar. I'll call it little b because it will be the partner of A. And B plus IS is actually a complex coordinate on the symmetric space. On the symmetric space SL2R, the thing you all know and you practice a lot in string theory, for instance. And the point is that there is no way I know to explain why there should be an SL2R symmetry of the action and of the equations in 3 dimensions, after assuming the scaling is isometry, by looking at the 4-dimensional situation. So that's one thing Marc was mentioning. Why is it that, can we see a sign of SL2R in 4 dimensions already? There has been a lot of work by the German school and De Witt and Nicolai. I'm not convinced at all. You can add auxiliary fields, but I don't think they explain that. Maybe they will explain to me, but I don't understand. So the situation in the early 80s was a situation of tension between the BKL chaos and integrability, because we were looking for more and more symmetries. In fact, in 2 dimensions, we expected Katz-Moody affine symmetries, and we started to work on that. But on the other hand, it was known that there was chaos. And the question is, how is it reconcilable? If you have something integrable that lives on tori, how can it be completely integrable? How can it be chaotic? So first of all, there were two things I want to say. First of all, these scaling vectors we assume are actually commuting. So it's a compactification on the torus, not on a sphere, where most of the work was done on spheres for BKL, and actually more spaces were considered. But if you look at the full picture, it's a little bit more difficult. And the only thing I found reassuring is that it was known for many years already by mathematicians and physicists that if you look at geodesic flows on negative curvature surfaces, in particular constant negative surfaces, like this hyperboloid here, this is an hyperboloid, then you know this flow is ergodic. So this situation of flowing on SL2R divided by SO2 is both ergodic and symmetric. One flow is not symmetric, but the flows are exchanged by some symmetry. So the question is, how can you extend that to bigger symmetries, bigger chaos, or different kind of chaos? And there was this lax pair discovered by Dieter Maison in 1978. So as I said, Euler symmetry is the key to mystery, in my opinion. So what is it physically? It rotates a Schwarzschild black hole with a mass to a dual mass. What is a dual mass? Called not charge. You can think of it as a gravitational magnetic pole. It has some topology, of course, but the spins don't match, so it's only a partial analogy. Also, I want to stress that I want to distinguish SO2, which is this rotation between electric and magnetic charge we have seen before, and SL2, which is a three-dimensional group. So SL2 has SL2R has two more generators. One is the scaling, so the shift of B by a constant, because B is defined by some differential equation. So there is an integration constant. So one more generator. So you have two generators, SO2 and this constant. And the third generator is that if you do a rescaling, so if you do a Killing assumption on the one dimension, the rescaling of the dimension, because it's cyclic, is symmetry, but in 3 dimensions. So in 3 dimensions, if you have SO2, you have SL2R. But what I want to understand is if you can see SO2 already in 4 dimensions. Maybe I should pause for questions because this is going to be a little bit more group theoretical. So do you have any questions about group theory or algebras or physics? Do you want me to go back something? Or? Okay. So, yes. Yes.
So you will exhibit this, the last paragraph. You will exhibit that?
No, I think I did it, but without writing equations. So if a solution doesn't depend on x4, the symmetry that was lambda x4, x4 time is sent to lambda x4, it also acts on the tensors. So the tensors that existed in 4 dimensions had indices 4, which remain indices which become internal in 3 dimensions, and this lambda acts on them. That's the R star action that I'm talking about, and this is symmetry. So I should say this because it comes from general relativistic invariance. It's a coordinate representization. I should have said that, sorry. More generally, when you compactify from d dimension to d prime dimension, where d prime is smaller than d, you expect a GL d prime minus d symmetry. In string theory, or if you don't do full compactification, you do just, if you do compactification but not reduction, then for instance, if you have a torus, the symmetry of the torus is SL d prime d minus d prime comma z, kind of modular invariance, which is the symmetry of the string. It's part of the U-duality of the string that we understand, everybody understands, where there is also an analog of this SL2, which is more tricky. It's connected to zero volume tori, but I don't think it's completely clear. So I don't know if you want to hear that. well, I have plenty of time. So let me just explain in one slide what the Dinkin diagrams are and what the root analysis is. So if you have a Lie group or Lie algebra, so Lie algebra is just generators of a Lie group, and you have to decide if the coefficients, the angles, are real or complex, or it could be quaternionic or something else. And the point is that Killing and later Cartons, Elie Cartons, had the idea that maybe you look at the generators as what we would call in physics observables, Hermitian observables in the case of unitary representations, and you want to diagonalize a maximal number of them, commuting. And the maximal number of commuting diagonalizable observables for a simple group, or simple Lie-algebra, is what's called the Cartons of Algebra. So now this diagonalization typically can be done over C because the eigenvalues tend to be complex. If you want to restrict to real numbers and real eigenvalues, you can do it, but it's more complicated. And the Cartons subalgebra has two parts. One will be fully diagonalizable, and the rest is to be treated differently. So this is called the Titsateke diagram. I will just mention some of the features later on, but I don't have time to explain. So one thing I want to say is that if you start from this SL2C, for instance, but also from a complex simple algebra, you have these commutational relations with coefficients in C, because you are over C. But the classification showed that you can select the generators to have only real coefficients, in fact, integer coefficients. So you can define SL2C, choose a basis where it defines SL2R, and of course the converse is trivial, you replace R by C, and you can even define SL2Z. Chevalier groups are also defined using these presentations, but they are for the groups, and they are for finite fields. So this restriction of the field, like here between SLNC and SLNR, gives you what's called a split form of UN. And the split form is precisely you can choose the Cartons generators in the same number of the full Cartons generator in the complex case. You can still do the root analysis, but all the eigenvalues are real. So you close your eyes, you do it over R. You are not allowed to, but it works. But in fact, in supergravities, especially for 6 spin-off supersymmetries in 4 dimensions, I will mention that example later, you don't have this real form that's split, so it's a little bit more complicated. You need this Titsatake construction. I think it's dead. No. So we have seen E8, but the story doesn't stop here, otherwise there will be no lecture. And the first idea was to go to E9. So the guy who first mentioned it to the community was a mathematician from Yale, Howard Garland, very nice man, who first looked at this E87 picture we had and said, but the next one is E9, and E9 is affine E8, so it's a Kac-Moody extension of E8. If you want, in other words, it's a gauge algebra of E8 over a circle plus a central extension. Central extension is important to get representations that are not too badly behaved with highest weight and so on. And so the question is, nobody had seen that before. Kac-Moody algebras were just being discovered and worked on at Yale. So he was one of the experts on the subject. In fact, he was working on arithmetic Kac-Moody groups at the time. But in physics, it took some time before we could understand it. And in 1981, I looked at what's called the gauge group. So the gauge group is the following. He took a situation pure Einstein in 4 dimensions and reduced to 2 dimensions. And you can do it by using any pair of Killing vectors you want. Each Killing vector gives you one SL2. And the construction of gauge was just to take all the SL2s, but an infinite number of them, one parameter family. So what I did is to exhibit one of these SL2s and another SL2 which was different, which was transformations acting on the 2 internal coordinates, and show that there was a central charge, precisely like the so-called Weil transformation, that would exactly fit to get a fine A1. But I couldn't check at the time, and still now it's not completely checked. Probably it's not true without extra constructions. That the relations which I found we are the only ones. And there was also one important thing which I stressed, which nobody else listened to, and many people said something wrong right now. Even in the work of Gerosh, who did this preliminary work on the group without knowing what it could be, he noticed that if you have two such killing vectors, so two directions, and you want to see if they're compatible. So is the SL2 of one killing vector preserving the symmetry of the other? And in order to have this commutativity of symmetries, in order to be able to combine these symmetries, you need two angles to vanish. So you are not talking about the full set of solutions, it's a zero codimension 2 subset. And this bad news for people who want this to be completely integrable, but they didn't listen.
So the Gerosh group is in this notation A11, affine A1.
If I was right, but in my paper I showed what I had done. I also said it was very difficult and not finished, but since then it's still not finished. I did another paper with Denis Bernard, and it was done by other people as well, using the dressing method, and we found some quantum algebra that seems to play a role. But the point is that in these constructions, you need to go from a finite set of fields to an infinite set of auxiliary fields, and there is no rule of what to do, what is best. And so it's almost impossible to say that A11 will never be a symmetry. Another example of that is sometimes you have learned about non-associativity, and because octagons are fashionable. Excuse me. I'm told that all the cases of interesting physics non-associativity are actually foldings of situations where associativity is restored. So you can very well guess or hope that this quantum group is just looking at a smaller projection of something that's actually a normal group, a usual group. But that I don't know.
So this function that Gerosh has to set equal to 0 to...
It's constants, two constants.
Constants, yes, sorry. Maybe that what could go beyond that by allowing non-local transformations. Or is this? Because I think that...
But the transformations are non-local because you solve this typically this duality equations where df is star dg already for... So I wanted to discuss more non-locality, but I didn't have time. I mentioned maybe a few words. So here I give you the U-dualities as they are observed in the supergravity. So this is the n equals 8. Should be careful. N equals 8 column going down from 11 dimensions. So 11 minus d is 0 to 10, 9, up to 3 dimensions, E8. The second subgroup is maximal compact subgroup, SO16, which I mentioned, or A7, which I mentioned too. Then the affine, which I put a question mark because it's not proved. And it's not really a triangle, but what you see is quite striking and it's not completely understood, is that here, the symmetry in 6 dimensions for n equals 8 is the same after complexification. So it's a different real form, but after complexification, is E6 as the case of n equals 5 and dimension 3.
The color code there, I mean, you have green, you have...
I forgot. I think this is a magic square.
Okay.
It's actually just a small part because there is no F4. So if you look at the series of groups, you have E8, E7, E6. In the magic square, I will show it maybe later. You will get F4 here. And you will get a square like this. But this slot is missing, like many other slots, because if you do, as I said, real forms, it's quite tricky. And it tends to cancel things. There is a version of our triangle, which is almost symmetric, which I may also show at the end. So what I mentioned before is that these symmetries here are not totally split. So the real rank of this E7 is 4, I think. And it decreases by 1 every time you go up in dimension because it's an internal torus dimension that becomes a Cartons of Algebra.
The number of supersymmetries is...
So, you remember n equals 6, so that's 6 times 4, becomes n equals 7, but n equals 7 is automatically n equals 8 because of CPT condition. So there is no n equals 7 if you want. Still, it follows linearly. I mean, it's one rank up. But there are many accidents in many places. So, any questions on that?
The ones which are not split, because
so most of them are not split. So I think.
The top one is again split. No?
So this column is split. Yeah, the top one is split. Maybe the next one as well, but most of them not. So let me show you this non-split situation. So I start with E7 in 3 dimensions, and I distinguished with open circles the so-called non-compact generators. So the real rank is 4. So this is the extended root. So forget for the moment this open dots. So E7, the static diagram is this thing here, and you get 4 non-compact R generator in the torus and 3 U1s. Okay. And you can diagonalize only these 4. And the question is, can you find an SLN inside this group? And how big is it? So you can certainly find SL4. But in fact, there is a trick that if you go to the affine diagram, extension of a group, as I said, the regular subalgebras can be obtained by looking at subdiagrams of that. But it's also true for the real forms sometimes. And if this root is non-compact, and this root is taken non-compact, then this SL5 is actually inside E7. So what happens is that if you go back up in dimension, so some kind is called oxidation of inverse dimensional reduction, what you do is to, instead of cutting this extra root, you cut one step higher, and this corresponds to building up the internal space, these torus directions. And the torus directions become larger and larger. And if you cannot go more than this, because this is compact, so it cannot be a SLN generator, which is split, then you know that you cannot get a torus larger than that. Okay? So you cannot go up to 11 dimensions. So it's quite interesting to know. In a way, it's inspired by Kac-Moody affine, but it doesn't prove that Kac-Moody affine is a symmetry, just because I was led to it by other things that I found it useful. I discussed with Tits, who invented these things, and was useful. So this is the same. So just one more word. I have said several times that what happens here is that you build up the torus internal dimension by going up, and so the torus shrinks. The torus increases, I'm sorry, going one rank up. And this is focusing on non-compact generators because it's Tits-Satake theory. There's another theory where you focus your attention on compact generators. So you look at the Carton torus and in the real forms, there are several Carton torus that may not be the same. And there is a Carton torus that's maximally compact, even for a non-compact group. It's not completely compact usually, but it may be almost. And that's what I want to do. And I claim that instead of building up the SLN leg, the one that corresponds to compactification of gravity on a torus, here I'm building up a leg, so I should say that, say in 4 dimensions, I'm talking now about going at 4 dimensions, going from n equals 8 to n equals 7, 6, 5, 4, and so on. And you see that, so the yellow is compact, blue is non-compact, there's only one, and sometimes there is D1 that's also compact. And this linear growth or decrease is exactly the same as before, but instead of occurring on SLN, it occurs on SUN in 4 dimensions. These are the R symmetry groups. So it's very interesting to see, but the symmetry between the columns and the lines I mentioned before have to change this sign, or this SL2 into SU2s, which is not an easy or free thing to do. And for dimension 3, the R dualities are SO2n. There are more theories, so it's more complicated, but the theories we have in this triangle, because they come from 4 dimensions, they have only those. And you get a similar picture. For higher dimensions, structure is not rich enough, and you have foldings. These arrows are talking about foldings, like you also had for Titsatake diagrams. So I can make sense of that at the moment. So after E8, E9 comes E10, and this was a result of this conference in Chicago, because we discussed a lot with Igor Frankl, and I mentioned some papers of NAM and what I was doing, and he was actually constructing the representation of A1 hyperbolic, and this is what's called sometimes overextended A1, and because of this SLN construction, if you go down to 2 dimensions, you would just add one root, and you would get the extended affine diagram, provided it's a symmetry, and construct this SLN, the full SLN, maximal SLN you can, which is just the right dimension for 2 dimensions compactification. And if you go to 1 dimension, then if you still want to extend this SLN, you will add one root in the Deakin diagram in the same direction. That's what I call overextension. And this name that Victor Katz took in his book, I think. So what they were doing is looking at A1. The affine A1 is 2 roots with special bonds. And the overextended A1, there's some arbitrariness, but I defined it to be just adding one simple bond and one more root. And that's precisely the group they were working on. It was mentioned by Marc, so I will not spoil his pleasure. So I will just mention that this group has a marvelous Weyl group. I will not tell you what it is, but you may work at it on that as an exercise. So another question, this should be in red, sorry, is here. So E10 is one of the 4 highest rank hyperbolic Kac-Modelli algebras. 2 more occur in string theory, D8 overextended and B8 overextended. So you remember what I mean. D8, you take affine D8, and you add one root after the affine root. Same for B8. But there is one more, which is the same as B8, but changing the sign of the arrow. And that group is pretty weird. I could never make sense of it in string theory, so I'm sure it should be somewhere. It should be interesting, but I don't know. So what did I do? I put a lot more E8s, more exceptions. Now, there's one, so I have half an hour, so it's pretty good. So do you want to ask questions, because it's a bit different now? Any questions on this? So what was proved for E10, of course the success with E10 was not at the time, because although some people believe that E9 was correct and maybe E10 was trivial, because of these angles I never quite believed it. And so I just systematically tried to understand what could happen if it was playing a role. But the only place where it actually plays a role is this Weyl group of E10 in the work of Marc and collaborators. And the Weyl group of A1 overextended in the paper I joined for the pure gravity case in 4 dimensions.
For this fourth algebra, the Weyl group is the same as the one of overextended B8.
I think so.
I mean, for the problem to find a place for the fourth algebra?
Yeah, yes, but in your case, I'm not sure. Yes, I think so. Yeah, right, sure. Okay, so the question is B8 actually seen? So even that is not completely clear. I think it's important in type 1 strings because B8 is SO17. Because the real rank works out this way, and also for heterotic strings, B8 or overextended B8 affine is important. But so D8 is important for type 2 string. 2B string. Sorry. No. D8 is important for type 1, and B8 is important for heterotic. That's what I want to say. Excuse me. So this is not just to have fun with group theory. Is it useful for equations? Can we simplify the equations? They are rather painful, long, and typically the situation in this job is you start with very awful equations. Like for instance, you start from 11 dimension. The 11-dimensional supergravity, it deals with 32 by 32 gamma matrices, but There's only a finite small number of fields, and the construction is manageable. We did it actually after some years of practice, but in a few weeks, once we decided to do 11-dimensional supergravity. For reduction to 4 dimensions, it's much more complicated. And what happens is that your institution where the symmetry is broken. So as you may expect, everything is complicated because the equations are all different. And then you want to restore the symmetry. And if you restore the symmetry, equations become the same, and the equations become much simpler. But the hard part is to restore the symmetry. So you have to pay once for all a hard price. And then, so the question is, can you restore more symmetries? And I claim, if I look at the P forms, I think I've written too much here. So I'll leave you read it slowly. So one thing I wanted to add just as a parenthesis is that it's actually Hawking that told me that this E8 and E9 story of ours in supergravity was extremely similar to the gravity case, pure gravity case, which of course he didn't know what the gauge group was either, but it was infinite dimensional, that's what he knew. And so it was quite encouraging, and it still is encouraging because it tells you that what you are doing for string theory, which is kind of theoretical object at the moment, is applicable to pure gravity and conversely. So we are within physics. So what I claim is that you can put all the P forms together in a supergroup element, which I call W, which will be the exponential of a superalgebra generator times some angle. The coefficients are actually the fields, the Grassmann algebra of the differential form of space-time that will group together all the P forms from the scalars, which are 0 forms, to the others. There's a subtlety that you need a Z grading in this construction, which is compatible with Z2's grading of the superalgebra. So just take even integers and odd integers as these two classes. But the grading for Z is more important, and maybe that explains why construction in physics is not really well recognized by superalgebras. If you look at this Z grading, maybe you will get a different classification. I don't know. This should be in red. So let me start with 11-dimensional supergravity in 11 dimensions. What are the generators of this algebra W, which make the group element W, which you should think of as a super sigma model field? So I start backwards, so it's here. So you have a 3-form A, coupled to them 2 braid, excuse me. A dual 6-form B, and we introduce, that's the restoration of symmetry part, a completely trivial superalgebra, QQ is equal to R, where Q is the generator coupled to A and R is the generator coupled to B. So W is exponential AQ plus BR. So A is a differential form of degree 3, so it's odd. Q is odd, so it's this group-like positivity. In the usual construction of supergroup elements, you need this parity to combine this way. And BR are both even, so it's okay. And then the twisted self-duality equation is universal for all these models we have considered. And it looks like this. So it's a sigma model thing, where this G minus 1 dg is equal to the dual of itself. Of course, this is in any dimension and forms of different degrees mixed, because W has several degrees, but it all works out. And there is another nice feature, is that there is a kind of invariant acting on these W's, which is chosen in each case in such a way that S star squared is 1. You remember that Hodge squared is 1 or minus 1, so depending on signature on the dimension, you may have or not have self-dual forms. With this S, you can do it in any dimension, and you do that. So this equation and this computational relation leads to the nonlinear term in G, which you may know. And so this equation is completely trivial. If you expand it in components, you get these usual equations which are doable but more complicated. I can tell you that if you do that for 4-dimensional n equals 8, there is such a group structure. It's a kind of Borchers version of E8. in 3 dimensions or in 4 dimensions. It's a Borch's versions of E7, and you still find all these expressions and all the equations combining that. So there is only gravity on the side, and I focus on the bosons here. The philosophy for the fermions is that the fermions transform only under maximal compact subgroups. I think some lectures will be devoted to that at the end, some seminars. So for me, although I said before that fermions are fundamental to explain all these mysteries, for instance, SO8 is important. So triality and fermions are quite important to explain why E8 might appear. But in the detail, in the structure of the action, the couplings are almost as simple as couplings of fermions in curved space. Once you introduce a moving frame, you close your eyes and you roll using Lorentz subalgebra and so on. This is exactly the same, but on internal dimensions. So let me go to the CP1 case, which is 2B in 10 dimensions. And the generators of this algebra are purely even because there are only form potentials that are of degree of even order for 2B. And there's a 2x2 Carton matrix, which is actually Borch's because one of the diagonal elements is 0, which encodes all the commutation relations of all the forms. One sees some kind of peculiar symmetry with respect to middle dimension with Hodge star. It's related to star duality because we are in complex geometry, algebraic geometry even. And here is a diagram. So just 1 minute, I have time. Oop. So let me just recall what you know about SU3, for instance. This is the positive generators of the Lie algebra. So Borch's algebra is an infinite dimensional Lie algebra, which is an extension of generalization of Katz-Moody, which even in Katz's opinion are more important than his Katz-Moody algebras. So he used to say, I don't know what he says today, but that in Katz-Moody theory, the most interesting part is affine Katz-Moody. And all the others, including hyperbolic, have been extremely disappointing to him. And that's why going from, for instance, hyperbolic Katz-Moody to Borch's by some extension was crucial to get the string model and the monstrous moonshine and so on. So I don't know what the situation will be. Maybe you will contradict me on that. We'll see.
Then E11 would be even worse.
Yeah, E11 is even worse, sure. Yeah. So if you know about SU3, which I am sure you know, this is the positive part of SU3. So positive roots is one generator here and one generator there, the commutator here, and then the symmetric and the Carton in the center. So the situation is because it's a different Carton matrix, this is 0 here. So these are bosonic generators, but there's no, it's completely different. So instead of closing, it re-expands again after D3. So there are two kinds of symmetries. There is a symmetry with respect to the center of the algebra between positive and negative degrees. As usual, I didn't draw them, but it's completely symmetrical. And there is a kind of partial symmetry. If you truncate into these two lines, you see that this central point is actually in dimension 4 for 4 forms, which are transverse dimension in 10 dimensions. And that's the dimension where you have self-duality. So here, for instance, you have the generator coupled to fundamental string, the D1 string. The dual is D5 strings, and this is the self-dual D3 string. So all the commutators are encoded by this stupid 2x2 matrix. I will not talk more about that. We can say things about real form. I don't think we have solved the question of 2B, of 2A or type 1 strings. It should be interesting, but I think we are, so I should have put it in right. My feeling is that to make these ideas of intersection forms and Cartan matrix as a geometrical object work, it seems that we are missing some dimensions. So an even greater symmetry, larger symmetry should be at work, because, for instance, there is some systematics about a mistake. The 2B case works fine, but all the family case, there is one family generator that has to be replaced, one has to be replaced by a 0. So there is some systematics, and my hope is that something quite big is waiting for us. So I mentioned the Inline Discovery in 1856. So Bouillon and Bouquet were students of Cauchy and of Liouville, probably here. And they did classify what is one maybe should call Panevet equation of the first order, so first differential order. The Panevet equations you may know are second order equations. And they had to solve this stupid equation here for any value of n, sum of pi minus 1 over pi is equal to 2. So you shouldn't confuse with what Marx, maybe there is a relation, but I'm not sure. Here, in any case, pi's are integers. And I claim this equation is much better than that one. And if you look at solutions of that one, you will get E6, E7, E8, and maybe AN or whatever. Affine, all affine. But if you add this one, you allow for D4 affine. But that's the equations they found in this Panevet analysis of the equations. So what they found is PQR is 632, and in this language, and PQR is 532 is what would correspond to E8 in the case of spherical symmetry group. So maybe I should pause a little bit. Forgot what I put to explain. Okay, maybe I do the previous slide and so another piece of physics that you may not know, the number of plane crystallographic groups in 2 dimensions is 17. So it's much smaller than 3. And it was actually classified about the same time, end of 19th century. And the way to encode these groups is by some generators. And 5 of these groups have Coxeter type generators. 5 more are their even subgroups, that is, you only look at even number of reflections, so it's a subgroup. And it's plain crystallographic group if you look at a root system that's affine, because affine is infinite, and as you may know, the Weyl group of affine groups contains translations. And there are 7 more that are more difficult to explain. And the 4 given below corresponds to E9, E81, E71, and so E71, E61, and D41.
So the plane crystallographic groups corresponding to E9?
Yeah, so I'll explain what I mean. Yeah. Sorry. Okay, I claim this is a Platonic E9. So the relation is the same thing that you may have learned in so-called ADE correspondence. The ADE correspondence, you have a deep correspondence, which can be analyzed systematically now, between simply laced groups and simple singularities in the complex surfaces. And the relation is as follows. Let me do it for E9. So let's look at the symmetries of this one picture here. You see that it has points of symmetry of degree 6, a mirror also of the same, points of symmetries of degree 3, and points of the symmetry of degree 2. And there's a general theory of these groups, which lead to this crystallographic construction as well. And because there is a mirror, you put a star, and this is describing completely the group. The relation, which is easy to draw, but not so easy to explain, is that why is it coupled to E9 or related to E9? Because if you look at the linking diagram of E9 and you count the number of dots until the vertex, there needs to be 1 vertex and 3 legs or 4 legs in the case of D4. Then if you count including the central vertex, you get 6, 3, and 2. Now if you did the same for E8 affine, which would be ignoring that root, drop this, then you will get 5, 3, 2. And this is one of the spherical symmetry group. So you get a crystal on the sphere. Crystal, it's finite crystal.
But so it's not the solution of the equation you wrote, or is it 1 over...
Yes, it is. 1 over 6 plus 1 over 3 plus 1 over 2 is equal to 1.
Yeah, but the other one?
No, it's positive. So these are the so-called finite dimensional one. Okay. So usual conditions for finite groups is that something is positive, strictly, affine is 0, and the others are partly negative. So I want to show you that in this picture, there's a crystal corresponding to a fine D4. Probably this was not discovered by Briot and Bouquet, but by some Persian artists long ago. I don't know.
So to hold any solution 1 over 2, here you have 1 over 2, 1 plus 1 over 2, 1 over 2.
This corresponds to the Cox-theta groups. As I said, the crystallographic groups.
Will have some nice
there is some relation for the. You can treat the whole thing, but it's a theory that has been not very well explained in print. It's due to I forgot his name. Some Spanish guy who was the equivalent of Turing, except he was cracking the Japanese code, and not the German code. And he was quite smart. And that was actually taken up by Thurston and Conway more recently. So it's quite fascinating to read, but and it's quite deep. It's connected to orbifolds. So I am arriving at the end, and I have 10 minutes, so I can comment, and maybe you can choose a subject if you're not exhausted. I wanted very much to stress the duality between chaos and integrability, and almost didn't talk about chaos. There are some slides at the end, but I want to show that, in fact, in the case of number theory, people, if you remember, are talking about random matrices for the zeros of the zeta function, and people are doing huge tests with huge, very high zeros, very large number of zeros, to see whether or not the Riemann hypothesis is correct. But in fact, there seems to be a conflict between what happens on the prime side, which could be disordered or not completely disordered, and the zero side, which is also somewhat disordered, but maybe not completely, because the fact that they are in Fourier duality, it's not quite possible to have both of them totally random. Just the fact that they are dual says something very strong. But nobody has been able to make this precise, to, for instance, disprove the Riemann hypothesis. So some mathematicians are quite skeptical, and even Dyson, towards the end of his life, was making propaganda for this story. So I leave it to you to read. Tonzaghe is a famous mathematician, combinatorician, algebraic geometer, guy who has very powerful experience with computers. And he says exactly what I just said. Primes grow like weeds. There seems to be no other law than chance. And nobody can predict what the next one will sprout. But there are many things you can say about pairs of primes along some conjugacy classes, modulo some integer and so on. And he says immediately, primes are even more astounding, for they exhibit stunning regularity. There are laws, they obey these laws. So I will maybe just give you the list of problems I proposed. So I wanted to talk about disorder, and I'm not clear about the following question. In Ising model, you have an order parameter, and you have a disorder variable, but because of the duality, disorder variable is a different order variable. So is there in the middle something that's really the disorder? And what is in the middle is the fermion. And this is quite a general picture. Maybe it's a little bit like this for prime numbers. So I wanted to make it more precise, but just some beginning. So I will not talk about that. So fermions are important in this. Fermions are order times disorder. Singularities are important. We heard about them. ED are actually singularities. So these are the allusion to Charybdis and Scylla, which were dangerous for Ulysses because one was a whirlpool, vortex, and this was a rock, or the opposite. I have prepared some general mention of analytic number theory, but maybe if I have just a short time, I will propose to recall for you which things I didn't know before, that you can actually classify real numbers in more than 3 classes, or 4 classes, rational, algebraic, and transcendental. There are more. KM theory is the beginning of understanding of chaos and disorder, but I could talk about it, but not so exciting. Quasi-crystals, they are not completely defined mathematically, but these numbers, these funny numbers, are important there. So I wanted to explain that, but again, it would be a full lecture. Arithmetical chaos is also quite important. Quantization and classical limits, I wanted to say something that's deep and close to my heart, which is to say that it's more important to understand in a given quantum theory what the quantum limit, the classical limits are, in particular if there are two of them, they can be in duality, in fact. It's even better if they are in S-duality. But the quantization problem, I mean, people have been trying that for many years, and we know that there is no functor. There are many ambiguities, which I also look for here. But my claim is that because we know that classical limits are not unique, at least in the best theories we know, we might say that there is no classical world, because well, this world would be better than that one. One classical world would be appropriate to some kind of range of values of parameters in an experiment, and the other would be interesting in a different set of values. But the real theory is the quantum theory. And the reason we can do that is that you have h bar, some h bar, should put it there. Sometimes it's called 1 over n. But it's not because you have an h bar that there is a unique way to have this h bar. For instance, if you look at the duality between electricity and magnetism, there is a duality between the limit h bar going to 0, keeping electric charge fixed, which is a particle limit, or keeping the magnetic charge fixed, which is the field theory limit of the electric degrees of freedom. And this particle limit has not been studied completely, and I also work on that. I wanted to finish a paper for Proceedings of the Royal Society a few months ago, but I'm doing other things, and it's difficult. I think it's quite important to. So the catchword is this duality is duality between electric particles and magnetic particles, but it's also the same duality between electric particles and electric waves. In other words, electric waves are the same, are on the same side as magnetic particles. Exercise, so it's not a problem because I know the solution. In 1897, what was discovered? Was the electron discovered? Was the electron wave discovered? And then you will know the answer for next time. I'll give the answer to Marc.
But sometimes people say that there is no classical limit.
Why?
Because, I mean, h bar, if you want, would be in the numerator and denominator.
I don't know what you mean. I think there are many classical limits. I can work on many of them. And the classical limits from second quantized field theory to classical field theory is pretty simple. So it explains, for instance, why, if you look at Young-Mills theory, the magnetic charge of the monopole is quantized, or is discrete. But it's h bar over E, and there is no h bar because it's classical field theory.
Then maybe I can formulate the question differently. Sometimes people say that there are theories without a Lagrangian because there is no classical limit.
Okay, that's a different story, yes. So I have sympathy for that. My self-duality equation is falling under that. Yeah, I don't know. But it goes the same way. It says that you should look at the quantum theory for sure.
Nature is quantum.
Yeah.